Hello and welcome to this lecture on neural network training using backpropagation. In this lecture we will conclude our discussion on the backpropagation algorithm and motivate some interesting variants of neural networks. So recall our discussion on feed forward neural networks where the flow of data is from the input layer and through the hidden layer to through other hidden layers finally to the output layer. So this is the forward aspect of neural networks. However, for training a neural network we need to be able to update the weights in the intermediate layers as well. So given a fixed structure, given a fixed number of output units and given the choice of a smooth sigmoidal function, we are going to discuss how the intermediate weights, the weights in the hidden layers for a neural network can be updated through something called backpropagation. So this is the high level overview of backpropagation algorithm. You randomly initialize the weights for all the layers and for all pairs of perceptrons between two layers. One does forward propagation to get the prediction for any specific example from the data set, and then you execute backpropagation. Typically this is done on any misclassified example from the data set. The backpropagation is by computing partial derivatives on every weight Wij. The partial derivative is computed for the error function EW, and one uses gradient descent to minimize the non-convex EW as a function of parameters W, and with that intent updates the weight parameters. One continues this till the cost function EW has reduced significantly. Once the reduction is significant, one might still resort to some random perturbation of weights W. This is because the EW may not be convex and one might want to avoid local minima. So here is the pictorial depiction of the backpropagation algorithm. The output layer is what interacts directly with the loss function. In other words, the loss function is evaluated at the output layer. However, in order to be able to update weights in the intermediate layers, the hidden layers, one needs to be able to reflect or impute the updates based on corrections in the output layer. So this is imputed updates on hidden layers. So this is what forms the backbone of the backpropagation algorithm. So the notation for backpropagation will be as follows. We will use sum JL to denote the sum over all the inputs from the previous layer L minus 1 weighted by weights connecting the corresponding input from the L minus 1th layer to the activation unit in the Lth layer. So we will denote an arbitrary activation unit in the L minus 1th layer by sigma I L minus 1 and an arbitrary activation unit in the Lth layer will be denoted by sigma j L. So the sum is going to be a weighted sum over the sigma I L minus 1, I ranging from 1 to SL minus 1, and the weights will be Wij(L). This will again recur in the following layers. Recall the objective to be minimized. It is basically a combination of the cross entropy error function this error function is computed at the output layer which is layer corresponding to capital L that we see here. We are talking about the activation outputs at sigma k L, capital L. The second component of the error is regularization. This regularization penalty is applied on Wij(L) for all values of L. Please note that the cross entropy function is indeed a function of all the intermediate layers, but only indirectly. So it will be more appropriate to say that the error E is a function of sigma with an arbitrary index k at the Lth layer, but sigma kl itself is a function of the sigma k prime at the L minus 1th layer, which itself is a function of all the sigma k double primes. It will be more appropriate to denote these indices as sets, and so on until you reach sigma p, set of indices p at the L plus 1th layer, which is a function of sigma at the Lth layer with an index that we adopt j. So this relation is indirect, and specifically we can encode this relation as follows: sigma p L plus 1 is the activation function g applied to the sum, the weighted sum, which we found to be L equals j equals 1 to SL of Wjp L plus 1 times sigma jl. So this is the same relation at every layer. So to compute the partial derivative of E with respect to Wij, which is mainly the update of interest, we are going to invoke a chain rule. So the partial derivative of E with respect to Wij(L) is a partial derivative of E with respect to sigma jl. The reason is that the sigma jl is what helps you reflect Wij(L) into E. So recall that sigma jl or sigma L is a sigmoid function or any activation function applied to the sum, which in turn depends on the W's. So we multiply this partial derivative with the partial derivative of sigma with respect to the sum, and then the partial derivative of sum with respect to the W. So this is fairly intuitive. However, what turns out to be challenging is computing the partial derivative of E with respect to sigma jl. The other two partial derivatives are fairly straightforward. The first one in blue is repeated from what we found in the logistic regression model, and it turns out to be sigma JL into 1 minus sigma JL. The second component is even easier. The partial derivative of the weighted sum with respect to a specific weight is the specific input sigma I L minus 1. So backpropagation is all about computing the first component here, and to compute this partial derivative, we again recall what we discussed in the previous slide. E is a function of the sigma at the Lth layer, which is a function of the sigma at the L minus 1th layer, and so on, which is a function of the sigma at small l plus 1th layer, which is a function of the sigma at j at the Lth layer. So the way we will compute this partial derivative is by computing the partial derivative of error with respect to the next layer, which is sigma p L plus 1. So it will turn out that sigma e, the partial derivative of e with respect to sigma j L will basically involve a summation over all the p of the partial derivative of e with respect to sigma p L plus 1 into, of course, the partial derivative of sigma p L plus 1 with respect to sigma JL. However, based on this representation of the error function as a cascade or a composition of functions involving sigma, one would expect that the second component would further be a summation over some p prime of the partial derivative of e with respect to sigma p prime L plus 2 multiplied by the partial derivative of sigma p prime L plus 2 with respect to sigma at the L plus 1th layer with index p, and so on. So this, we expect this to continue until the output layer. This is the basis of backpropagation. So we will consider this for a single example xy. This is basically in the spirit of stochastic gradient descent. Where we will update Wij based on the error computed for a single example xy viewed as a function of w's with respect to Wij. So we have dropped the outer summation, and here's our backpropagation. The partial derivative of e with respect to sigma JL is sum over p indices onto the perceptrons, activation units of the L plus 1th layer, of the partial derivative of e with respect to sigma p L plus 1 multiplied by the partial derivative of sigma p L plus 1 with respect to sigma JL. What we have done here is expanded on this partial derivative. So this corresponds to the partial derivative of sigma p L plus 1 with respect to sigma JL. And we especially note that since sigma p l plus 1 has dependence on sigma j l through the sum p l plus 1, we can further apply this chain rule. What we have done here is substituted a simple expression, the partial derivative of the sum at L plus 1th layer on the pth node with respect to sigma jl, which comes from the previous layer, is just the weight connecting the jth node of the lth layer with the pth node of the L plus 1th layer. For the output layer, however, we have a much simpler expression, and it turns out that given the direct dependence on the output layer, this expression is very similar to a single node neural network, or in other words the logistic regression model. So we can recall this expression for logistic regression model. So here is backpropagation in action. So what we find is the partial derivative of E with respect to sigma jl is being derived from the partial derivatives of E with respect to sigma pl plus 1 of the previous layer. So we have made an implicit assumption that a whole lot of these partial derivatives from the previous layer are computed and supplied to this node. At this node you have a weighted linear combination of these. These are assimilated for updating the weight. So the update basically invokes the chain rule, and we now know the value of sigma j, the partial derivative of sigma jl with respect to sum jl. We know this to be sigma jl into 1 minus sigma jl. Likewise, we know the expression for the second partial derivative as sigma I l minus 1. So we substitute these, and what do we get? So we get this following backpropagation update rule. The update step is a product involving sigma from the lth layer, sigma I from the L minus 1th layer, multiplied by the backpropagated partial derivative of E with respect to sigma jl. Now applying this update to get the new weight vector, we get sigma wijl is wijl minus eta times this partial derivative of E with respect to wijl, and here is the overall update rule. This is the backpropagation algorithm for training the neural network. We recall that you implement forward propagation on every example to find its class. For every misclassified example, you execute backpropagation, and you do this by performing gradient descent. How you do that is elaborated below. You start with the last layer, thereafter you go down up to L equals 2 and use the computations of the later layers into the preceding layers. So we are just putting together a whole bunch of computations. The partial derivative of E with respect to wij involves by chain rule the partial derivative of E with respect to sigma j from the nth layer into the partial derivative of the sigma j L with respect to the sum at the nth layer or at the jth node, and the partial derivative of the sum with respect to Wij, which is sigma IL minus 1. There is an additional component which comes from the regularizer, which we have temporarily missed out, and that basically will amount to the shrinking parameter minus lambda. It will be a minus lambda times Wijl. These iterations are continued till there are misclassified examples. For inseparable data sets, there will always be misclassified examples. So you continue until there is significant reduction in the error function. When no more significant reduction in the error function is possible, one might stop. In practice, one often resorts to some random permutation of the weights and restart a couple of times, go over the entire algorithm from the scratch. This is primarily to counter non-convex nature of the error function. So the error function that we have discussed, which is regularized cross entropy, when evaluated across the weights on all layers, turns out to be non-convex. It can have multiple local minima. So the goal of random perturbations of weights to restart is to help move from possible local minima, possible valley, into a point that coincides with descent direction for some other valley. And the hope is that this new point leads you to a better valley. Since that may not be the case always, you might need to do this restart a couple of times. There are of course several tweaks and variants associated with these restarts. Now, there are certain challenges in neural network training, and we can just list a couple of them. There are several challenges that can be associated with neural network training. So despite our effort to counter the local minima through random restarts and perturbations, we are still not guaranteed to find the global optimal. So though we have used random restarts because of local optima, only approximately correct solutions are often found. A second concern is, how do you design the architecture? How many layers? How many nodes per layer? What kind of activation functions? These are all challenges in designing any neural network for a specified problem. Very closely associated with this challenge is the challenge of associating semantics with the neural network. What does the first hidden layer correspond to? What do subsequent hidden layers correspond to? Often one might want to associate semantics in retrospect, which is after learning the weights. There are also other challenges such as numerical precision errors. You have lots of multiplications and additions, and especially with activation units like sigmoid, where with numbers between 0 and 1 you can land up with very small numbers, especially during backpropagation. Of course, one of the biggest challenges is computational issues. Computation to be performed, how much of it can be parallelized, how much of it can leverage memorization or caching. Could some of the multiplications of weight vectors with sigmas be memoized across nodes or across layers? Finally, we have the trade-off between complexity of the model. This involves the complexity of the architecture as well as the weights associated, and there is a trade-off between this complexity and learnability. So given a complex model and given infinite amount of data, it might be possible to learn very complex functions, but the issue is our data might be limited. And in fact, as the model becomes more complex, one might require more data to learn the same model that one might learn with a less complex model using the same amount of data or less amount of data. So we have the curse of dimensionality that complex models will incur. So as the number of parameters become large, one might require more than a linear factor growth in the size of the data in order to be able to learn effectively. What changed with neural networks over time? So the origin of neural networks can be attributed to the computational model of threshold logic. This was in 1943 by Warren McCullough and Walter Pitts. For a long time there was some kind of saturation in results obtained for tasks such as ImageNet using neural networks. So the best numbers in 2011 for ImageNet was around 75%. In 2012 the numbers jumped to 85%, it's a big jump, and in 2015 the best known numbers are 96.5%. These are comparable to human level accuracy. What changed in such a short span of time? There were many challenges associated with boosting the numbers from 75% to 96.5%. These include the ability to deal with varied background, having the same object in different colors. For example, you can have a greyish cat and a blackish cat, varied sizes and postures of the same object, varied illumination conditions and so on. And these issues do crop up in other tasks such as optical character recognition, speech recognition. However, with certain advances in neural networks, we are today able to address these tasks without any significant signal processing overhead or domain knowledge. For example, speech recognition is now possible without segmenting the word, or in the case of image recognition, without segmenting the image into components. One can see the change in this table. The ability to deal with 16 by 16 images in 1989 grew to 28 by 28 images in 1998, and 2012 it's much larger. The number of units that these networks have had has also grown by very large factors, practically orders of magnitude. The number of connections, the number of parameters, all of them have changed, and in fact the activation units have also changed over time. So one of the primary reasons for being able to do so well has been the use of advanced computing infrastructure, and one of them is the GPU, the graphical processing unit. So one can see the number of operations that these modern networks are capable of handling because of GPUs. There are of course several other reasons for this advance. Some of them include better architecture design, for example, several modern neural network architectures do parameter sharing, and we will see the example of parameter sharing in convolutional neural networks. There are also other techniques such as pre-training for example, would involve training or learning the weights of the initial few layers of the neural network in an unsupervised manner. So supervised data might be hard to get, but there are lots of unsupervised data sets, and one could use this unsupervised data to get a warm start and learn effective weights on the initial hidden layers. So there were several algorithms that have been developed in the past, but many of them became effective with modern features and advances in machine learning paradigms, which include pre-training. Of course, one of the important reasons for advance was also large amount of data, and this can be attributed to regular competition, evaluation metrics, and several challenging problem statements. We already mentioned this, but advances in computational resources cannot be undermined. GPUs and industrial scale clusters. Of course, tasks have also become more challenging. The number of classes have increased, and we also started looking at class spaces that have structures. An example being sequence prediction. We will end with an example. The convolutional neural network is an instance of a neural network which has parameter sharing along with a very specific structural bias. So far, the backpropagation algorithm we discussed involved fully connected layer, which means every node in every layer was connected to every other node in the subsequent layer. One might make some structural assumptions and connect a node in one layer to only certain subset of nodes in the other layer, for example the adjacent nodes. So this is called a locally connected layer. However, even within this locally connected layer, one can make assumptions on the weights. So one could assume that the green edges here, which follow some kind of pattern, share the same weight, and so do the red edges which follow another pattern. So convolutional neural network has much smaller number of parameters due to local connections and weight sharing. However, this is hinged upon the structure of the problem. Convolutional neural networks been found to be very useful with image recognition, where this local structure can make a big difference. We will discuss more on this in the coming lecture. Thank you.